So let's talk a little bit about the Internet of Things and figure out what's going on in this world. And the first thing to note is the Internet of Things is not well defined. And when I say that, what I mean is everybody has their own definition of what the Internet of Things is. This is the ITU definition. It says it's a global infrastructure for the information society, enabling advanced services by interconnecting physical and virtual things based on existing and evolving interoperable information and communication technologies. Well, that sounds nice, doesn't it? Let's simplify it. The Internet of Things is things that use Internet technologies. That's the Internet of Things in a nutshell. It's things that use Internet technologies. Now, they may communicate across the Internet that we know as the Internet, or they may simply communicate using Internet technologies like IP, TCP, message broking technologies, and so forth. So the thing about the IoT is that one device that is an IoT device is not necessarily the same as another device that is an IoT device. Some IoT devices have sensors in them, some do not. Some IoT devices interact with their environment and some do not. Some IoT devices monitor their environment and have no interaction with the environment, while others both monitor and interact with the environment. So there's a lot of complexity in it. But one of the ways that they're generally defined is the goal of an Internet of Things ecosystem is to provide anytime, any place, and anything access. To accomplish that, there is a lot of complexity involved because you have to have the right protocol to make it happen. 802.11, for example, is not the perfect protocol for everything that wants to be on the Internet. And so you have to have the right protocol to make it happen. You have to have the right supporting architecture or ecosystem to make it happen. And so there can be a lot of complexity in IoT when you get outside of that consumer space where you're just dealing with a single building, a single house. When you're in that consumer space, or what we call residential IoT, in case you don't know, the acronym for that is RIOT, because that's what's going to happen when you start implementing consumer devices in the enterprise space. You're going to have a riot when the OT people come to the IT people and they all get out in the parking lot and the groups are on each side and they come together. Well, okay, hopefully that doesn't happen. But there is a big problem we're facing right now with consumer devices coming into enterprise. Because consumer devices, I want to be as formal as I can so I can have respect for 7 Signal because I really like to respect 7 Signal, but I've already come in with a t-shirt. So for that reason, I'm just going to say consumer devices tend to suck. And they tend to not be manufactured with good components. They tend to not be manufactured with security in mind. And that's why we have some 43,000 MQTT servers sitting out on the internet that just anybody can go and take a look at and find out what's going on with people's IoT systems, because they're not implemented with security in mind. So with that said, let's start talking a little bit about where it came from and where it's going. The history of IoT, of course, we first really used the term in 1999 when an individual from Procter & Gamble said that they were developing Internet of Things solutions within their company. His name was Kevin Ashton. And that was the first use of the term, but it wasn't the first use of the technology. So the concept that is Internet of Things was around for longer than that. In 2005, the ITU published an IoT report really saying, okay, this is a formal concept we're going to talk about now. And then the first major conference was in 2008. Also, because of that major conference and other things that happened that year, 2008 is often considered the birth of IoT. It's the birth of IoT from the perspective of everyone started talking about it. But it's not necessarily the birth of IoT from the perspective of what it is. An IoT device is a computing device that uses network protocols to communicate. That's really what an IoT device is. So it's not anything new, but how we use that concept is what is new. And how massive it is what is new. And the fact that so many of them use wireless now instead of wired connections is what is new. So why do they implement IoT? I found this very interesting. The number one reasons organizations implement IoT is to save money. They don't do it to make money as the primary reason. They do it to save money. So you've got to keep this in mind when you're implementing IoT. You've got to step back and ask yourself, what am I doing with my IoT implementation that's helping save money? Because we always know it's a primary driver. A second factor, though, is to make money. 35% roughly want to make money. Then 24% care about their people. So the other people, we either save money or make money, and 24% care about their people. And they say, well, it's about safety. That's why we're implementing it. Well, in seriousness, though, the major drivers are these three. These are the major drivers that make people want to implement IoT. They want to save money, make money, or improve safety. And so if you take those three drivers in relation to your IoT implementations and ask, how am I accomplishing those things, you're very likely to be meeting the objectives of that particular organization. Because that's what, according to research, is driving the vast majority of IoT implementations, and particularly in industrial IoT. But when we look at the markets where IoT is being deployed, it's all over the place. We've got industrial IoT, oil and gas, human IoT with wearables and body area networks, healthcare, retail, and the list goes on and on. There are all kinds of areas where there's specialty IoT, and a lot of these have their own acronyms, and a lot of them fight with each other about who gets to have the acronym. Because you've got, for example, Internet of Military Things and Internet of Medical Things. Who wins? I don't know. But both of them call themselves IOMT. So you're going to run into all kinds of new acronyms to you when you start to look at IoT, because everybody wants to take IoT and turn it into their own personal acronym as if their deployment is entirely uniquely different from anybody else's deployment. And then shockingly, when you actually look at what they deploy, it's a pretty typical architecture, implemented in a pretty typical way. And when you understand those typical architectures, you can wrap your mind about how to get IoT to work for you. So what are these things that we need to think about when implementing industrial IoT, for example? Well, first of all, we have the building blocks that allow us to accomplish our end goals of IoT, like decentralized intelligence. So we do not want to have all intelligence at the center. Why would that be? Why in industrial IoT, or possibly in transportation IoT or other verticals, do I want to decentralize intelligence? It's because of decision making. It's because decision making needs to happen in milliseconds. And I can't rely on central intelligence to make a decision in milliseconds when I've got 30, 40 milliseconds of latency between the device that's going to take action and the place where the decision making is being made. And so when I need instantaneous decision making, like stopping a conveyor belt, or if I'm dealing with a self-driving truck in a mining operation and I want that truck to stop immediately, it's not okay for that to go back to the cloud, and then the cloud thinks for a little while, makes a decision, reports back to the truck, hey, you should stop. By that point, it's already crashed into the wall or the other piece of machinery or whatever it happens to be. So I need decentralized intelligence. I need intelligence at the edge. And that's one of the things that we look at when we're implementing IoT. Where does the decision making need to happen with my IoT devices? I also need rapid connectivity. Not necessarily fast transfer speeds, but the ability to get connected quickly, transfer whatever I do need to transfer or receive, and then get off the network. Think, for example, of driving through a toll booth. So, any of you ever drive through toll booths? Maybe you have like an Easy Pass or something like that, right? Well, what if you had to wait for, let's take the 802.11 world. I've got to wait for open system authentication. I've got to wait for association. I've got to wait for EAP TLS processes to complete. I've got to do a four-way handshake. And now I can transfer information with the Easy Pass system and decide whether I'm allowed to go through that toll booth or not. Now, what has already happened? I've already flown through the toll booth and set off alarms because it's taking too long, right? So I need to get on fast, validate that I actually have a valid Easy Pass subscription, and move right on through and be billed later on. So therefore, sometimes you need that kind of rapid connectivity in order for a device to connect wherever it happens to be, do the communications it needs to do, get off the network. And as much as possible, I want open standards and systems. So I want to use technologies that are not proprietary, that are not closed, so that I actually know what's going on with my network. The only way you can really troubleshoot a network or design a network well is if you know how that network works. And once again, another opportunity to give credit to Seven Signal, because they help us a lot in that troubleshooting area, particularly, as well as design and growth predictions. So the primary benefits that comes out of these three building blocks is real-time context integration. I have instant data analysis because I can do it at the edge. I don't have to rely on central intelligence in the cloud or even in a localized server. and therefore I have no delay in efficiency adjustments in the context that I'm in. So, for example, if there's a temperature change that needs to take place within a facility, the decision to do that happens immediately. So if you go back far enough, you go back decades ago, a person has to walk up, look at a thermometer on the wall, and determine the temperature of the room, and do I need to make adjustments? And then they physically make the adjustments. And then eventually it becomes to, well, we can have temperature sensors connected through SCADA systems that are connected to our HVAC system, and we can have that operate, all through serial cables or different buses and different technologies to allow it to happen. But today now with wireless, we have the ability to make that wireless too. And so now we have the ability to put that on the same network that other sensors are on, having consistency in our environment at the edge network, or what's sometimes called the proximity network, and making it so that all that data can be aggregated together for even better decision management in the future of our operations and better efficiency. But real-time context integration is key. And not only from a single sensor, but we have the opportunity for sensor fusion, so that we can not only detect that the temperature is higher than it should be in a room, but we can also detect that there's a particular machine that is running hotter in that room than it should be because of the rate at which it's running. So we know it's running hot, we know it's running at a higher rate than it should. We take those factors all together, and we know the real decision that we need to make is related to that machine, because the machine is running hot because of running at too high of a pace, and we can slow that machine down. So sensor fusion says we're bringing sensors together from multiple devices, and we're analyzing all of that data to truly understand what's taking place within that space. And because of the fact that we can aggregate the data together, not only can we have the instantaneous decisions, but we can make better long-term decisions through big data analysis over the trends that we see in our environment over a long period of time. Where do we need to invest in the future, for example, to gain efficiencies in operations and so on? And then finally, we have autonomous behavior. Now, this is a really big thing. Autonomous behavior is where the edge is making really important decisions, like the edge is deciding, for example, where a truck in a mining operation is going to go next. And this can be based on sensors that are analyzing whatever's being mined, or rock or gravel or sand or whatever is being created there. Where is the next area where the truck needs to go to pick up a load based on what's being produced in the different areas within the mining operation? All of this can happen without a human making a decision, because there are sensors at all of the different locations. We might be sensing how large a pile has become, using things that can detect proximity and range and the existence of objects within a space, and utilizing computer vision and so forth. We can detect how large that pile is, and do we need a truck to come over there yet? And when we do, the truck is automatically routed to that destination for its next pickup. And then, of course, going to where it's going next. And you might say, but you're talking about a dream world. This sounds like Terminator. Well, it's not a dream world. It's real. It's here right now. This kind of thing is happening right now in mining operations and so forth, where they're already implementing these types of autonomous vehicles, because if we get humans out of the way, it's a safe space to do it, right? The reason we don't have self-driving cars on the highway yet is because of risk of life. We can't just throw them out there and let's say, well, we'll fix it as we find errors when there are crashes, right? So we can't just say, hey, we think we've got it all right. We've got to know we've got it all right once you put several million humans out on the interstate system all at the same time in self-driving vehicles. So the first stage is assisted driving. Let's see how that goes. And well, there have been some crashes, right? So we've got to deal with those problems. We've got to fix the algorithms. We've got to fix the sensor systems. We've got to get it good enough for assisted driving before we dare go to autonomous or self-driving vehicles. But in spaces where humans are not present and risk of life is not present, we can be a little bit more flexible in what we're implementing. And in something like a mining operation, we can get by with a little more than we would on a typical highway. So we're already beginning to see a lot of these things being implemented. Now, when we talk about IoT, one of the things we want to think about is platform operations. The reason we think about this is because it simplifies development of IoT solutions, and it provides consistency across our IoT solutions. So for example, if we choose a particular platform at the hardware level, we're deciding what our platform is going to be at the hardware level. What we're talking about is the sensors we're using, the actuators. Sensors detect things in the environment, right? Actuators interact with the environment. They do something in that environment. Printed circuit board, the PCB, it's the board that the sensors and actuators are connected to so that they can get some compute intelligence, maybe have storage, maybe have networking connectivity and so forth with Wi-Fi or other types of networking modules. So we standardize on that hardware layer, and what that means is that then we come up to the operating system layer, we can have consistency, because if there's an operating system that supports that hardware layer and we always use that hardware layer, we've got consistency of the operating system we're using. And then we can also have consistency in APIs, which becomes key. Application programming interfaces give us the ability to get these systems integrated so that they're working together in their operations. And then that takes us up to the software level, where we've got logic or rules and control and even more APIs and policies that are all deciding what's going to happen at those lower layers. This is where the intelligence resides for our sensor network. And so if we've got some consistency in that area, we're better off. And this is what platform-based IoT is all about. It's about trying to develop some consistency. Some of this comes through standards, and some of it comes through selective vendor choices. So when we're building out our network, we're choosing vendors that share a platform. Maybe they use the same protocol. Maybe all of these vendors are using ZigBee, for example. Maybe all the vendors that we choose are using Z-Wave in some type of a small business deployment or what have you. So the key is that we're choosing a consistent platform, and by doing so, we already know we have some level of consistency in the data that we're going to have at the top level, meaning that we can aggregate that data more easily, make better decisions out of that data, and use that information for our business operations. Now, when you get to practical IoT, where the rubber meets the road, you're talking about the individual IoT devices, the networking, and then the management of that information that's coming across the network. So IoT devices include, of course, sensor devices. They include controlled devices. You know, like some of you might have smart light bulbs in your house. Any of you have smart light bulbs? I'm sorry. I don't want anything smarter than me in my house, so I don't have smart light bulbs. But no, we've got smart light bulbs, we've got smart thermostats, we've got motion detecting security cameras in our houses now, or doorbells that are motion detecting security cameras. So, you know, we've got all this intelligence that we're putting into our homes. Well, in the enterprise space, we have all that and then a whole lot more, right? So we have many types of devices out there that fit into this IoT category, sensors and non-sensor devices. When it comes to networking, there are all types of networking components we might use. There's the cloud. Many people like to use the cloud. Does anyone know what the cloud is? No, we don't. We just use it. But it's a fluffy object in your network diagram, right? Linux servers, yes, that's it. There you go. The cloud is a bunch of Linux servers. So the cloud obviously is the thing where we say, we don't care how you do it, just give it to us. And don't care what server we're accessing, it's just out there for us. But many of the solutions that are out there use the cloud. So the monitoring may happen in the cloud. It may happen locally and be reported back to the cloud, but cloud is often used. 802.11, obviously an IoT protocol that can be utilized, can connect to the existing 802.11 wireless networks you already have. 802.15.4 is a very common foundation protocol. It defines the lower layers of communication. So the actual way to get data across radio frequency waves is defined, and the way to format that data is defined. We're talking about the physical layer and the MAC layer within communications. ZigBee is an example of a technology that's built on top of 802.15.4. Bluetooth is another one, really gaining some steam now because of a couple of things. Because of Bluetooth mesh being introduced, giving the ability to build mesh networks with Bluetooth protocols. Also because of the newer Bluetooth 5 offering angle of arrival and angle of departure location capabilities so that we have more accurate location down to centimeter levels. These types of things have made Bluetooth very interesting and appealing to people in the last 3 to 5 years. And so there are a lot of predictions out there when you just look at the predictive statistics that say that Bluetooth is going to become one of, if not the dominant IoT protocol within the next 5 years or so. So there's a lot of trending going in that direction. Of course, there's cellular connectivity. You know, you've got a sensor or some other IoT device you want way out in a remote area where there's no other network coverage that you're providing, but you want to be able to get data from that device back to your applications or to the cloud. Cellular networks are a great way to do that, as long as they, of course, have coverage in that area. And there are all kinds of cellular networks. We won't get into the excruciating details of them here, but many different types, and some that are designed just for IoT, like LTE-M and NB-IoT and so forth. Sigfox and LoRaWAN are examples of WAN technologies that you'll have to find a service provider that enables you to utilize them, or you can implement your own in the case of LoRaWAN and build out your wide area network connections. Of course, all these devices can connect with wired, but we don't want to talk about that. This is the CWNP conference here that we're about to start. So then the next thing is, of course, analytics and control. So whatever of those networking technologies we're using, ultimately, we may have mobile phones, we may have smartwatches, we may have tablets and laptops and other computers that we're using to access all of that monitoring data. The beauty of IoT is that we can put the devices where we need them, and then we can monitor it wherever we need that. And so if I want to get notifications on my smartwatch, and by the way, I have a new smartwatch. It's the most expensive one that you can get. It's invisible. It's got cloaking techniques, so you can't even see it. Phenomenal device, and it alerts me anytime I'm making a bad joke. So the point is that smartwatches, what are they? Well, they're little computing devices on your wrist, right? And by the way, they're IoT devices themselves. But they can receive alerts based on the other devices that you have. So you can literally right up to the second get an alert of something really urgent that you need to know about right there on your wrist. You can go into more advanced applications then on your phone to take a look at deeper analytic details to see what's going on with that situation. And then you realize, oh man, I've got to whip out my laptop. I've got to do some configuration changes with the apps that I only have there. The point is, you have localized access wherever you are to what you need when you need it, because everything's going to some central location, whether that's the cloud or your own internal systems that you're using to communicate with these remote monitoring and analysis devices. Now, here's the big thing. Where are we at with IoT deployments? So you can do a Greenfield deployment or you can do a Brownfield deployment. We'll not talk about the details of why one is called a Greenfield and one is called a Brownfield, but let's just say that a Greenfield deployment has no existing systems and a Brownfield deployment may already have some crap in there. I mean, it may already have some IoT devices in there, okay? So the difference between the two is obviously, in a Greenfield deployment, I'm empowered. I get to pick every little detail of what I'm going to implement, right? In a Brownfield deployment, I've got to support what's there. And so I've got to make sure that what's there keeps functioning if I need to keep it there and functioning while I'm also implementing the new. So I can't be implementing something that's going to interfere in the same frequency space, cause problems in that frequency space, and so forth. And so when you look at the different verticals, you can kind of get a feel for where you might run into a Greenfield or be more likely to. So in a home environment, you're more likely to find a Greenfield deployment there, especially if it's an older home, right? Not recently built, or a home that has people in it that are less tech savvy. But the general speaking guideline is that residential IoT is more likely to be Greenfield than enterprise IoT, okay? But also smaller businesses may not have as many IoT devices, as many different wireless protocols running. Agriculture, it's just kind of the new thing for them in the last few years to start implementing it, so more likelihood there. Hospitality leans more toward the Brownfield side than any of these, but you may be able to find some Greenfield there. Particularly, there's a hotel at exit off of Highway 33 near where I live, where it intersects with Highway 42. There's a hotel there that is a Greenfield deployment because it's been empty for 10 years. It's not working. The Brownfield deployments, where there's already a lot of stuff, transportation, even more in enterprise and healthcare, even more in industrial, and so we certainly see all of these things already exist there. So where it falls on that spectrum, this is not an exact science, these are just giving you an idea of where things fall in that range for IoT deployments. So how do we plan out this IoT deployment, these IoT devices we're going to be implementing? Well, there are a lot of different models that can be utilized to conceptualize how IoT is implemented. For example, we have the IoT WF model. This is from the IoT World Forum, when they all got together and said, we need to come up with something that's going to give us a good model to live by, and they came up with a 7-layer model. We have probably a good 24 different frameworks or models out there now that each one considers itself to be the best model. And you can look through them and you will find some commonalities that we can scale down, and we can say, what if we want to simplify this? If we simplify it, we come up with this 3-layer model. That we've got an area that's about perception, an area that's about the network, and an area that's about applications. And when we think of it from that perspective, the sensing or perception layer is where we have the edge devices, right? They are either interacting with the environment or they're reading information from the environment and so forth. Then we have the network layer. How do we get the stuff that they're either reading to the rest of the world, or how do we get the commands from the rest of the world to them for actuation? And so the network layer gives us the communication. And then we have the application layer, which is where we have our analysis, whether it be analysis of long-term historic trends through big data, or it's analysis of a message that just came in and do I need to take some action? Okay, so perception, network, application can greatly simplify this perspective. And I want to be clear, this is not something that's an origination with CWNP. This simplified 3-layer model was developed by others to simplify those couple of dozen other IoT models and help you wrap your minds around the big things you need to focus on. So how are my edge devices going to function? What intelligence are they going to have and so forth? How are they going to communicate with the internet that they're supposed to be a thing on? And what applications are going to be in charge of monitoring, controlling, and managing these different devices? And that brings us to the IoT hardware. Now we have a picture here of a Raspberry Pi, which is a good maker board. It's good for evaluating and testing the solution that you're trying to build. And if you're building it just for yourself, it can even become the end solution platform. If you are instead yourself a manufacturer who's going to be manufacturing 50,000 units, or maybe you hope 500,000 units, right? You're going to be the next big thing. Then in that case, this is probably not the best board to use to make your device, because you're going to need to be able to keep getting the board for a few years, right, as you continue manufacturing. So you do have to keep that kind of thing in mind. Therefore, when you purchase an IoT device, take it apart, look inside. If you see a Raspberry Pi device as the main board, that's probably not something that someone thinks they're going to sell 500,000 of. And if you know you're going to need 50,000 of them over the next 10 years in your project, you might want to step back and ask yourself if that's the right vendor for you. Otherwise, don't take it apart. Just go to the FCC, look up the FCC ID, look at the internal photos, and see what's inside of there. And that way you don't have to worry about taking it apart. But either way, watch out for the components they're built from. Because when something is built from kind of hobbyist maker board components, it can be assigned to you that they might not be able to fill your need if you are going to be dealing with a very large project and you need many thousands of components in your project. But it's great for when you need that unique thing. And sometimes you need something that nobody sells. It's that simple. You may need a specific combination of sensors at one location and you want one device to have those sensors and nobody sells it. And so either you put 3 devices at that location or you go and make your own device that can go to that location, or possibly 75 different locations where you want that. So it's definitely possible to make your own IoT device, and it's not that hard. You know, a lot of companies do custom software development. Today, what we're going to start to see is a lot of companies doing custom IoT hardware software development, because the difference between where we are now and where we were 20 years ago, when you wanted to build your own custom hardware software solution, I mean, you were looking at the only way to do that was to buy a full-blown computer and then write your own software for that full-blown computer and plug it into your wired network. Today, you can get, and you don't even have to go to this large of a maker board, you can get maker boards that are $29, put a wireless module on it, plug in a few sensors, and you've got a component that you need to accomplish your end goal. And so there are certainly options. And then the beauty of it is, when it comes to the radio, if you've already got, say, ZigBee or LoRaWAN or some other technology in your environment, You just buy the module that gives that to the module, to the component you're building, to the IoT device you're building. So you simply build it into your ecosystem, rather than having to say, well, the only one I can find out there uses a completely different protocol than we're using, so I guess I have to yield and now have a heterogeneous environment and mixed APIs and figure out how to get all this to work. Or you can build your own component that uses the exact same technology that you're already using. So there are a lot of options there. And one of the things we're going to see in the near future is consulting firms and organizations that specialize in just that. So you can outsource the custom build of your own IoT devices that you need. You'll tell them, I need 750 devices that do this. No one makes it. Give me a proposal for the cost of development, and they're going to be building these projects out for people at cost-effective levels, probably more cost-effective than they could do it in-house, because they're already going to have their own custom software for reading data from sensors, communicate on the network. Everything's already there. They're just kind of tweaking and customizing it to fit your specific need. Now, here's the big thing. Here's the scary thing with IoT. Security. The reason it's scary is so many manufacturers don't think about it. Because they want to rush to market, they want to get it out there into the market space, they want to start selling module or units, and they want to start making money. And so security becomes an afterthought. And security is not a light thing to be considered. So I've got here just a few little examples of some incidents over the last couple of years. Xfinity security system flaw allows sneak attacks by jamming radio frequency. What's that talking about? That's talking about a home security system that worked on 2.4 gigahertz, and all you had to do was jam 2.4 gigahertz, and then you could break open any window or door you wanted, and none of the sensors would know it's happening. And so there was no alarm triggering. So all you had to do was jam the frequency. They didn't have it coded in that if connectivity is lost to the sensors, assume there's a problem. Instead, it was if connectivity is lost to the sensors, we're not getting an alert, must be okay. And that was the logic within the system. Not a good logic. Consumer IoT devices are compromising enterprise networks. In this report, they reported on the many thousands of IoT devices having been deployed in the enterprise space that are not implemented with security, either at the physical hardware level with root of trust security concepts, or even at the networking level. And then, of course, you can find tons of these articles on several ways that hackers can exploit vulnerabilities in IoT devices. The top IoT security problems reported, according to one research report, was open ports. If you don't know what that is, a port in TCP/IP communications for TCP or UDP at that level of communications just is a place for an application to receive communications, right? And so ports are open that are not needed by the device. Sometimes there's even services running behind those ports that aren't needed by the device. So if you've got some kind of monitoring solution that can look for open ports in your environment and give you reports on that, that can be beneficial. Poor authentication or just none. Unencrypted updates. So there's something common in IoT called firmware over the air, and a lot of IoT devices have been deployed out there that do firmware over the air with no encryption whatsoever while it's happening. Or even worse, they do configuration updates over the air without any encryption while they're doing configuration. And then there's the other channel in, right? These are Internet of Things. So internet-based attacks where we attack the things on the internet that the things off the internet talk to, like your data servers, your message queuing servers, and these types of things that can be a point of attack to give you information about the network. Where does wireless and IoT come together? Well, it comes together with the various different protocols that support it. For example, ZigBee is a very popular one in industry and other environments, and this is a protocol mostly implemented in 2.4 gigahertz, though it does support other frequency bands as well. The dominant is 2.4 for one simple reason. Does anyone know what that is? Actually, the lower frequencies give even more range. Yeah, exactly. It's universal, right? So the 2.4 gigahertz band is worldwide, and you can use that band. And therefore, hey, why not? We'll put our grill on it. We'll put our garage door opener on it. And by grill, I mean that thing you cook steaks on, by the way. We'll put our security cameras on it. We'll put every device we ever build onto 2.4 gigahertz. Why? Because it's worldwide, and it makes it easier, and it does make it easier for manufacturers to just limit it to 2.4 gigahertz. Their life is simplified. They don't have to have a different configuration or firmware for different regions of the world where the lower frequency bands may or may not be supported. And so ZigBee does support lower frequency bands, but here's the interesting thing that ZigBee has done to show they've given into the trend of using it almost only in 2.4 gigahertz. In all of their public-facing documentation that's easily accessible at their website, they simply say ZigBee works in 2.4 gigahertz. They don't even mention the other bands. When you go look at the actual specification, they're all still in there. They still support 900 megahertz, for example, 800 megahertz. It's in there, but the public-facing stuff that talks about the specs for ZigBee and how it works, it just says it works in 2.4 gigahertz. Because they've given in, they've yielded, that's where people use it. Now the good news is there are ways to get ZigBee and Wi-Fi to coexist together in the world of 2.4 gigahertz. That's a positive thing. They don't coexist perfectly, but they coexist better when designed well than they do when designed poorly. And so there are ways to work around some of those issues. But ZigBee is a very common one, and you can see in the diagram that it is based on 802.15.4. In the upper right, we have an example of a Bluetooth architecture or structure. Bluetooth varies greatly. There are a lot of different Bluetooth models or implementations that can be done. So we still support all the way back to at least Bluetooth 2.1 in many Bluetooth devices. So we've got a range of different physical layers and MAC layers and modulation methods and all of this that's used in Bluetooth. So it's a wildly varying Bluetooth is not Bluetooth thing. There are many different versions of it. So you got to make sure your Bluetooth is the Bluetooth you want it to be. If you want, for example, Bluetooth Low Energy or BLE, it's got to be 4.0 or above right out of the box. It can't be less than that or it won't be BLE. If you want Bluetooth mesh, you got to have the right chipset and so forth that gives you Bluetooth mesh. So you've got to be very careful with selectivity when dealing with Bluetooth because of that. Then we have other technologies like just 802.15.4 with something on top of it. So there are a lot of proprietary protocols that are based on 802.15.4. So they use the MAC and PHY, but then they build their own proprietary solutions above it. Sometimes they tell you it's 802.15.4, sometimes they don't. We have Z-Wave, which is mostly popular in consumer space, but it is making inroads into some enterprise space as well in most recent versions because they've enhanced the protocols. They've tried to make them more enterprise friendly because they want to compete more. Interestingly, Z-Wave at the Z-Wave Alliance has about 3 times as many member companies as the ZigBee Alliance has in their organization. And you might wonder, well, why is that? When ZigBee's used in enterprise, wouldn't it be a whole lot more popular? Well, actually, because it's consumer, think about it. The companies that are going to be involved can be, you know, like my garage. That's where they're manufacturing their devices, right? Because it's consumer space. And they're building that stuff that I talked about that's not necessarily of the utmost quality. Or it might be great quality, by the way, coming out of a garage. That's important to remember as well. It could very well be. In the history of computers, some great things came out of garages. And I'm not just talking about the cars the people that got rich in the computer revolution drove out of their garage. All right, so when we're looking at IoT then, here's what we have to consider. We have to think about how it's going to impact operations in our environment. And as I'm wrapping things up here for this presentation, I want to talk to you a little bit about a major conflict that's taking place in our businesses today. There is a pretty significant bit of tension between operations technology and information technology, the OT people and the IT people. Because historically, the OT people were in control of the plant. They were in control of the oil field. They were in control of all of that stuff that an engineer, well trained in that stuff, needed to deal with. And IT people stayed at the corporate headquarters, doggone it, and they stayed out of our way. And now we've got the pain point of these two groups coming together. And we've got fear elements involved. We've got OT people afraid that they're about to lose their job to some IT person that doesn't really understand plant operations. And guess what? They probably don't. And we've got IT people frustrated because of the lack of security in so many things that are being deployed in the plant. So we've got this dilemma, and what we need is we need to come together. We need to come together and realize that we need the expertise of plant operations, of field operations, of oil and gas operations, of the operations technology people that have been doing that forever. We need their expertise, and then to be able to do it the IoT way instead of SCADA and other older systems that have been traditionally used for this, we need the IT people, and we need their expertise. And I'll tell you a great big secret. The best way to bring the two together is to find a local authorized learning center and attend a Certified Wireless Solutions Administrator training class with CWNP. No, but seriously, you know, it's funny because I was just having a conversation last week with an individual from the Maricopa County college something organization. They manage something about all of the universities there, and I never fully grasped exactly how they manage it. But she was telling me about the demands that are being placed on them now for people coming out of their university programs. And the challenge that they're facing is having people well trained exactly at that point of junction between OT and IT. And trying to find people they can hire is next to impossible. And so what they're doing is they're literally bringing people from out of state and even out of country in to fill these job positions because they can't find the people that can integrate these two historic traditions of IT and OT and make them work well together. And so there is an important thing there to understand. There is an integration of these two things. And so what I would suggest to you is to really begin developing your OT folks in networking communications that are used in these wireless systems, and begin developing your IT folks in operations technology. Send them off to some training classes that teaches them about SCADA. You know, you might say, well, they don't need to know that. Well, they kind of do, because now they're going to be implementing IoT devices that are going to generate data, and SCADA systems are going to generate data, and we've got to bring it all together. We've got to find a way to collaborate and work together well and overcome this barrier that exists. So if we can get both sides educated on both sides, we can have a lot better solution moving forward and a lot less resistance to change, because a lot of that resistance to change comes because they're fearful of losing their old way of doing things. But if we can show them the new way is really cool, and that their skill sets help us do this really cool thing, and without their skill sets we can't do it, we can take this fear and resistance and turn it into excitement and momentum. And that's really what needs to happen for us to jump into the next stage. And the next stage is going to be massive. It's going to be huge. So if you're not ready for it, get ready. We're going to have tens of billions of devices over the next decade being deployed in industrial IoT and agricultural IoT and health IoT and all the rest. So get ready for it, and get ready for the need of what 7 Signal is going to evolve to be as well. And that is going to be an environment that can monitor whatever you're doing in wireless. Of course, I'm dictating to them what they're going to become, but they're going to give you the ability to monitor whatever you're doing in wireless, because that's what you're going to come back to them and tell them that you need. And so they're going to help you with that. And I'm confident in that prediction. You'll see. So I want to thank you for giving me the opportunity to come here today and talk to you a little bit about IoT. Thank you for letting me bring in my crew and to stand before you in our little fun t-shirts that we got yesterday. So I've enjoyed being here. If you ever have any questions, I'm easily available, tom@cwnp.com, so I'm easy to reach. That's tom@cwnp.com. I'm also available on Twitter @CarpenterTom, because some other person already took @TomCarpenter. So you can go out there and find me there. If you ever have any questions, you want to talk to me about something, figure out what's this or that problem I'm facing and I need help, feel free to contact me at any time. Thank you very much, and have a wonderful rest of your day.